Okay, we continue with trigonometry, and today we're talking about section 5.4. This is where we talk about right triangle trigonometry. So this is a lot more like what you've seen in high school. Our basic right triangle trigonometry, well, you need a right triangle. Okay, so if we look at a right triangle, we know it's a right triangle because we put this little symbol here, meaning it's a right angle. Okay. Now, the side opposite the right angle is always the hypotenuse. And we usually abbreviate that HYP. And let's say we have an angle here, alpha. Then we have two other sides. Okay. So the one across the way, like if you were to draw an angle, an arrow, this way, this would be known as the opposite side, which we'll abbreviate OPP. Okay, opposite. And then the remaining side is the adjacent. I think there's an A in there. Yeah. Okay, so remember from high school, many of you know this, SOHCAHTOA. So what that means then is that the sine of alpha is equal to the opposite over the hypotenuse, while the cosine, A and H, of alpha is equal to the adjacent over the hypotenuse. And finally, the tangent of alpha is equal to the opposite over the adjacent. And then, of course, if we want to take the reciprocal functions, so this one's cotangent, this one is secant, and this one's cosecant, then it's just the opposite. So it's the reciprocal, it's the hypotenuse over the opposite. This is the hypotenuse over the adjacent, and this is the adjacent over the hypotenuse. Okay. So let's do an example with these. Then let's say our triangle looks like this. And we are told that this is alpha. Then also that this is 7 and this is 3. Okay. And we're supposed to find all of the trig functions. Okay. So that is, we're supposed to find the sine of alpha, the cosine of alpha, the tangent of alpha. Then this one's the cotangent of alpha. This one is the the secant of alpha. Okay, so C and S. So this is S and C, and this is the cosecant of alpha. Well, we can do that. That's not a problem. We'll need to know what the opposite angle is. We know that, and the adjacent angle, but we don't know about the hypotenuse. But that's okay. We can use Pythagorean theorem. So we know that 7 squared plus 3 squared has to be equal to the hypotenuse squared, or that 49 plus 9 is equal to C squared, so 58 is equal to C squared, so that C will take the positive square root of 58. Because it's an actual triangle, we don't have negative lengths. Alright. So from there, we can just read, well, the sine is the opposite 3 over the hypotenuse. It's just the square root of 58. And we can rationalize these, but we don't need to right now. Okay. So the adjacent, it's got the cosine is the adjacent, 7 over the square root of 58. and the tangent is the opposite over the adjacent. Now for the reciprocals, we can just flip them. So this is 58 over 3, square root of 58 over 3. This is square root of 58 over 7, and the cotangent is 7/3. Now let's look at it this way. Let's say this is again 7 and this is 3, but now we want to find this angle, and we'll call it beta. The same will happen. We'll use the Pythagorean theorem to find out what the hypotenuse is, okay, or the remaining side. Okay. But now let's look at this. We're looking for the sine of beta, the cosine of beta, the tangent of beta, and let's see, this is tangent, so this is cotangent beta. C, so this is secant of beta. This one's S, so this was the cosecant of beta. Okay. So now when we're looking at this, the opposite side is 7. This is the opposite. While this side now is the adjacent. Okay. So the sine of beta is the opposite over the hypotenuse. The cosine of beta is the adjacent over the hypotenuse. The tangent is the opposite over the adjacent. And now we can take the reciprocals. The cosecant is square root of 58 over 7. The secant is square root of 58 over 3. And the cotangent is 3 over 7. So let's look at these two together now, okay? And there are some similarities, okay? Here I have 3 over the square root of 58, and here I have 3 over the square root of 58. So what we're really saying then is that 3 over the square root of 58 is equal to the cosine of beta, but that's also equal to the sine of alpha. And we'll see lots of similarities like this. Like here's 7 square roots over 7 over square root of 58. Okay. So what we have there is 7 over the square root of 58 is equal to the sine of beta, which is also equal to the cosine of alpha. And there are more. Okay. Here we have 3/7, the tangent of alpha. So I'll write that down. 3/7 is equal to the tangent of alpha. But we also see from here that that's equal to the cotangent of beta. And we can do the opposites here as well. Okay. 7/3 is equal to the cotangent of what is that? Cotangent alpha, and it's also equal to tangent of beta. Here we have the cosecant, and the secant. So this is square roots of 58 over 3 is equal to the cosecant of alpha, which is also equal to the secant beta. And lastly, here, we have the square root of 58 over 7 is equal to the secant of alpha, but that's also equal to the cosecant of beta. Okay. Alright, so this is what I have written down now. These are the relationships that we see. So let's think for a minute. I'll give you just a second to think about what these might have in common. And specifically, let's think, since these all involve alphas and betas, how is it that alpha and beta are related? I'll redraw the picture. So when we talk about alpha and beta, what we know is this. We know that alpha plus beta plus this being 90 degrees has to equal 180 degrees. That's because the sum of all of the angles in a triangle must add up to 180 degrees. Okay. Well, if I solve this for alpha and beta, I could subtract 90 from both sides. And what we'll see then is that alpha plus beta must add up to 90 degrees. And what this means then is any two angles that add up to 90 degrees are called complementary. So alpha and beta are complementary. So that's what we're looking at here. We're looking at angles that are complementary. Now let's see this relationship. Here I have sine, and here I have cosine. Same here. Sine and cosine. This relationship has tangent and cotangent. Similarly over here, tangent and cotangent. Here we have secant and cosecant. Same here, secant and cosecant. Okay. So these pairs, as we have matched them, these are known as cofunctions. Right? So sine and cosine, tangent and cotangent, and secant and cosecant. These are cofunctions. Oops. Cofunctions. Right. Now this is not the same as the reciprocal function at all. Okay? These are cofunctions. And what this leads to here is one of our biggest theorems. A theorem is something that has already been proven and we don't have to prove, we can just use the result. Okay? So I abbreviate theorems THM. Okay? And the big one from trigonometry is that cofunctions of complementary angles are equal. So what does this mean? Example. If I have the sine of 43 degrees, that has to be equal to the cosine because it is the cofunction of 90 minus 43 degrees, which is the cosine of 47 degrees. 48, yeah, 47 degrees. Okay? So the sine of 43 degrees equals the cosine of 47 degrees. Now these are in degrees. I, of course, can do it in a different way. I could look at the cosecant of pi over 7. Well, that has to be equal to its co-function. So the co-function to cosecant is secant. Now here we use 90 degrees, but I'm in radian measure now. So 90 degrees is pi over 2 in radian measure, minus this pi over 7. Okay. Now we can simplify this angle. Let's get a common denominator. I'll multiply by 7 and by 2. So this has to be the secant of, now over 14, 7 pi minus 2 pi. So this cosecant of pi over 7 must be equal to the secant of 5 pi over 14, because (5 pi over 14 plus pi over 7 equals pi over 2. That is, they are complementary, and these are co-functions. To see this, just multiply by 2. By 2. So we'll get 5 pi over 14 plus 2 pi over 14. Well, that's equal to 7 pi's over 14, which is pi over 2. So there's going to be questions in your homework and some on the exam that will ask you these both in radian measure, testing whether you know the theorem that cofunctions of complementary angles are equal. Okay. Now, let's think about what this could mean if we put it on in the units, well, not the unit circle, in the Cartesian plane, the xy plane. Okay, so let's say here's my x and here's my y. I'm going to pick some point out here, x over y. And I could draw a line from the origin to this point. And if I wanted to use this length as a circle, I could swing it around. So we could call this the radius. We will have created some angle here, alpha. And we can always create the right triangle by dropping an altitude. Well, if this is the point xy, that means I had to go some distance x, so we'll call this side of the circle x, and then I had to go up some distance y. Now notice r is not necessarily 1. Okay? Now let's find out what the sine of alpha is. Okay? Well, the sine of alpha has to be the opposite over the hypotenuse, y over r. Now if you're on a unit circle, notice r is 1. So we just have y divided by 1, which is just y, which is what we've been working with. Okay? The cosine of alpha is the adjacent over the hypotenuse, which is x over r. The tangent of alpha has to be the opposite over the adjacent, which is y over x. And then we can do the other functions. The cotangent of alpha then is the reciprocal x over y. The secant of alpha is r over x. And the cosecant of alpha is r over y. So, for example, let's find if the terminal side of alpha passes through -3, 6. Let's find the 6 trig functions. So let's redraw our diagram with that. Okay. So our diagram then now looks like I have this point, where does it go? -3, 6. Okay, so let's actually draw it like this. -3 and 6. Here's my point. Now it doesn't matter what quadrant it's in. I can still draw this triangle. Okay. And now to get there, this value is -3, okay, because we're headed in a negative direction, and this side is 6. Okay. So if I just knew what r was equal to, we could answer this question. Okay, so here we go. Using Pythagorean theorem, we know that -3 squared plus 6 squared has to equal r squared, or that +9 plus 36 equals r squared. 10 plus 10 would be 46, subtract 1 is 45, is equal to r squared. So r will be equal to the square root of 45. We'll take the positive because the radius is always positive. Okay, we'll take it that way. And we could simplify this radical, but we won't have to. So let's just do what we have. So let me redraw this so we can see it. Now this is square roots of 45. This is -3. And this is 6. Okay. So here's our angle. Okay. Now, we know that then the sine of alpha is equal to the opposite, which is 6, over the square root of 45. The cosine of alpha is the adjacent, which is negative here, representing a negative direction. And the tangent of alpha is the opposite, which is 6, over the adjacent, which is -3, which is -2. And then we can take the reciprocals. So the cotangent is equal to now -1/2, so reciprocal. The secant of alpha is, and I'm going to move this negative up top so we don't lose it, -45, square roots of 45 over 3. And the cosecant of alpha is square roots of 45 over 6. Okay, so your homework might ask you to simplify radicals, right? So let's do one example of that. Like, for example, the square root of 45, remember 45 is 9 times 5, so this is the same thing as 3 square roots of 5 over 6, okay, because the square root of 45 reduces to this. And then the 3 and the 6 will cancel, leaving square root of 5 over 2. Let's see how it works over here. -3 over, and remember square root of 45 is 3 square roots of 5. So now these will cancel, leaving with -1 over the square root of 5. Which, if we rationalize that, becomes negative square roots of 5 over 5. Okay. So just be aware of how your answer book is asking you to do these things. Okay. Now, so far we've worked with right triangles that are nicely oriented. It doesn't matter how they're oriented. We just need to talk about standard lettering. Standard lettering. Let's see if I can do it. Now let's say the right angle's here. Okay. The right angle is always going to be the capital letter C. Okay. And so the side opposite is always the small letter C. Now it doesn't matter what you pick after that. The angles will be labeled with capital letters. So let's call this angle A. Okay. Then the side opposite that side is represented by the small letter A. Then the remaining side we'll call capital B, and the side opposite that is small b. So, for example, let's say we had something that looked like that as well. Okay. Here's our right angle. Let's say they tell you this side is 9. This is angle C. And this side is equal to, I don't know, 15. I don't know if this will really form a triangle, but I'm just saying, for example. Okay. What that tells you then, and they want you to look for, to find the angles. And this is angle B. Okay. Then angle A, well, we know one thing. If this side is B, then this angle has to be capital B, which will force this to become angle A, the remaining angle. And that will make the side opposite it little a. A, B, and C. Okay, so that's how it might work. Let me find an example. Here. Okay. Of how we might be working with this. Okay. Alright, so, for example, let's say you're given A equals 10 and C equals 12. Then solve the right triangle. Okay, so the first thing to do is trying to understand what's happening. Okay? So you're going to have a right triangle because we're told it's right. So I'm just drawing a right triangle. Okay? Now I'm told that C is 12. I know that capital C is the right angle. So the side opposite that must be little c, which is equal to 12. Alright, well, now what? I have this other angle A, or I'm sorry, this other side A. So if I call this side A, that forces this angle by our standard lettering to be A, capital A. Then the only other angle that's left is capital B, which will force this side to be little b. Okay? That's just our standard lettering for it. Okay. Now when you're asked to solve, what that means is you want to find all the angles. Okay? the measure of all the angles, so we need to know what A, B, and C is. Now we're given C, we know that's 90 degrees. Okay? And remember your degree symbols. Okay? Otherwise you're saying it's in radian measure, and it's not true. Then our sides, we need to find little a, little b, and little c. Now, luckily we're given what little a is. It's 10, and we're given little c, which is 12. So let's see if we can find the other angles. Okay. Well, what do we know? I have a right triangle and I know two sides, so I could find B very easily by Pythagorean theorem. I know that a squared plus b squared must equal c squared, or that 10 squared plus b squared is equal to 12 squared, or that 100 plus b squared is equal to 144. So b squared is equal to 44. So b must be equal to, we'll take the positive root of 44. Okay. Which we could reduce to 2 roots of 11. Okay, so 2 roots of 11. The question then becomes, how are we going to find A and B? Okay, I know they have to add up to 90 degrees. That's true. Why? Because the sum of the angles must be 180, and if this one's 90, then the remaining sides, or I'm sorry, the remaining angles must add up to 90. But what do I know about these angles? I don't really know much. Okay. But I do know this. Okay. I know that if I look, I know that the sine of this angle A must be equal to the opposite over the hypotenuse. So what does this tell us? This tells us that the sine of this angle is this ratio. I could reduce it to 5/6. Okay. But I don't want what the sine is. I'm trying to find out what the angle itself is. Okay. So as an aside here, remember if I know if x squared is equal to 44, there was an inverse that undid the squaring. That is, that the square root would undo the squaring, so I'd just be left with x was equal to the square root of 44. We just took the positive root because of the it's an actual triangle. Okay. What else could we do that has inverses? If we had the cube root of x was equal to 2, we knew we could undo this. We could undo the cube root by taking its inverse and cubing it, okay, so that x would be equal to 8. We also know, let's come over here, that inverses can look very funny. We know if we had 2 to the x was equal to 7, we know that 2 to the x and the log base 2 of x are inverses. So we'd solve this by writing exponentially, but one thing we could have done is that I could have taken the log base 2 of both sides. Now, because these were inverses of one another, the log base 2 of 2 to the x, well, that was just x. And then we said x was equal to log base 2 of 7. Okay, so it was a bizarre way for us to get to this. It felt bizarre in the beginning. Okay. You could also look at this by writing it exponentially, and once you did that, writing logarithmically. Once you did that, you would get the same results, that the log x was equal to log base 2 of 7. Either way, x was in the exponent, and we needed to undo that, okay, so we could get to it. Okay. So now our unknown is wrapped up in a sine function. Okay. And so I'm going to just ask you to believe me that the trig functions do have an inverse. We're going to spend an entire section building up what they are. Okay. But what I could do, the inverse trig function is sine, and it looks like to the negative 1. Okay. So this is the inverse sine. If you take that of the sine, it will undo, and you'll just be left with your angle. And then your answer is just the inverse sine of 5 over 6. Okay. This is an angle. Okay. It is an exact value of an angle. Okay. We're not going to approximate these. Do not approximate these using your calculator. Right. So the inverse sine of angle A, well, angle A is the inverse sine of that ratio, 5 over 6. And this is how you'll be expected to answer it on your exam. Now the last one we have to find is just angle B. We know angle A and angle B were 90 degrees, so B has to be 90 degrees minus the inverse sine of 5 over 6, okay? Which is angle A. 90 minus angle A would be equal to B. Okay? So this is how we would solve. Okay. Okay. Now we need to talk about story problems. Let me just pull some up from the book so I can reference them for you. Okay, let's do number 292 from your book. Okay, so in angle 2, or in angle 2, in number 292, you're given that C is equal to 200, and angle B is equal to 5 degrees. Oops, sorry about this, number 292. Okay, so let's set up a triangle. These are right triangles. Okay. So this angle is angle C, the capital C, and the side opposite it is little c. We're told that angle B, it doesn't matter which one we pick, let's call this one angle B, that is 5 degrees, which forces this side to be little b. Then the remaining angle is A, and the side opposite of it is little a. Okay, so let's do this one. Right. We're supposed to solve this triangle, which means we're looking for all the angles and all of the sides. Okay. So we have angle A, angle B, and angle C. we're told that B is 5 degrees and C is 90 degrees. So, angle A and angle B are complementary, meaning they have to add up to 90 degrees. So angle A has to be 85 degrees. Okay. Now, for little a, let's see, the only thing we know is C is equal to 200. Okay. So what is the length of this side? Well, we now know that this is 85. So we know that the opposite over the hypotenuse, so that is the sine of A is equal to little a over 200. Okay. But we know more than that. We know the sine angle A is 85 degrees is equal to A over 200. And I'm looking for the value of A. Okay, so to do that, I can just multiply both sides by 200. Then these will cancel. And so A is equal to 200 times the sine of 85 degrees. Now, the sine of 85 degrees is not one of our known values on the unit circle. So this is an irrational number. And then as we write it like this is the exact value. And this is how you'll be writing it on your exams. So the side A is 200 times the sine of 85 degrees. And that's what you would just list there. Okay, now we're looking for angle B. So we know this now is 200 times the sine of 85 degrees. Okay, remember your degree symbols. Okay. Now when solving these, I like to use values that are given to us right away so we don't run into any approximation errors. So I know this one and I know this side and this is the opposite. So let's just use the sine again. That the sine of B, which is 5 degrees, has to be little b over 200. And then we can do the same thing and just multiply by 200. So these will cancel. So we can say that B is equal to 200 times the sine of 5 degrees. Again, the sine of 5 degrees is not one of our known angles on the unit circle. It's an irrational number. So we could just fill this in then as 200 times the sine of 5 degrees. And with that, we would have solved the triangle. I hope that makes sense. Let's do some more. Okay, let's do number 296. So in this case, here we have a triangle. This angle is 63 degrees. This angle is 39 degrees. They've dropped in altitude, therefore forming a right triangle. And they say the height of this altitude is 82. And what we're looking for is this side, x. So the question is, how do we go about it? This is no longer a right triangle. We can see that, let's see, 63 plus 39 is 12, 1 is 102 degrees. So 180 minus 102 degrees is 78 degrees. Okay, so this entire angle here is 78 degrees. So we do not have a right triangle in the entire place. But I do have a right triangle here. And I have another one here. So let's pull those out so we can look at it. So I know this angle's 39 degrees. I know this height's 82. I know this angle's 63 degrees. And this height is also 82, because they're the same altitude. Now these are right triangles. So what I'm looking for is the length of x, which is this side plus this side. So this is some x1, and this is some x2. But what we know about them is that x1 plus x2 has to equal this x, this entire side. Which is what we're looking for. Okay, so let's see what we can say. x1 is our unknown. Now this is an adjacent side, and this is an opposite side. Okay? So I could say the tangent of 63 degrees is equal to 82 over x1. Would be true. It's the opposite over the adjacent. The problem is I'm looking for x1, and I don't necessarily like having those in the denominator, my variable. So I could use this fact. The cotangent of 63 degrees is the reciprocal, which is x1 over 82. And what makes that nice then is if we multiply both sides by 82, these will cancel. So we have x1 is equal to 82 times the cotangent of 63 degrees. So that's one part. These cancel, 82 times the cotangent of 63 degrees. Okay, that's fine. So let's do the same over here. Again, we could look at, we know the opposite over the adjacent, so we know that the tangent of 39 degrees is 82 over x2. But we run into the same problem. So wouldn't it be easier just to say the cotangent of 39 degrees is equal to x2 over 82? So if we use the same logic and multiply by 82, we have 82 times the cotangent of 39 degrees must be equal to x2. So now we can complete the problem. We have that x is equal to x1 plus x2, but we know x1 from here is 82 cotangent of 63 degrees plus 82 the cotangent of 39 degrees. And so this is the value, without using a calculator, it is the exact value of the length of the sum of these two sides, which is what we were looking for. Okay. Now let's do 310. Okay. Now in 310, we have a big tree. It's a giant redwood, okay, growing off the ground. And in fact, it is 370 feet tall. Okay. Now, there's a person there, and they walk a certain distance. Okay, so that means they don't know how far they've walked. but they're going to measure the angle of elevation to the top of the tree. So this is the angle of elevation, and we are told that that is 60 degrees. So by drawing this diagram, what we have then is that there's a right triangle, okay? Because we'll assume that this tree is going vertically. Okay, let's pull that out so we can see it. So now this is 60 degrees, and this is 370 feet, and this is our unknown distance. I don't know how far away I walked, but it is 60 degrees. Okay? And that's exactly what they want to know. How far away from the base are you? Well, okay, now that we have that, we'll use the same idea. Again, I know the opposite over the adjacent, okay? So I could say the tangent of 60 degrees is equal to 370 over x. But let's make things simple on ourselves. We know what the tangent of 60 degrees is. Okay, so the tangent here at 60 degrees, this is the short side of the triangle over and then up the long side. Okay. So the tangent of 60 degrees is the sine of 60 degrees over the cosine of 60 degrees. Okay. That's equal to 370 over x. So the sine is square roots of 3 over 2 divided by 1/2. That's equal to 370 over x. And I could multiply by 2 over 2, then those will cancel and those will cancel. And I would simply have the square root of 3 over 1. So this is really just the square root of 3 is equal to 370 over x. Now x is in the denominator. We will need to get that out, so we'll multiply both sides by just x. Okay. So we'll cancel on this side. So we have 370 is equal to x times the square root of 3. And now we just have to divide by the square root of 3 to get x by itself. Those will cancel. And so as an exact value in feet, we are 370 divided by the square root of 3 feet away. Okay. So the difference is here, I knew what the tangent of 60 degrees was. So we then found the actual value before solving for x. Okay. All right. Let's do 302. Okay. You should be watching this video as you're trying to do your homework. Okay. To reference this. Okay, number 302. First of all, we have to set it up properly. Okay. All right. I have a monument some distance away, and we are told that it is 200 feet tall. Now, someplace there's a person in a window. We don't know how far away this person is, okay? But we know two things. If they look up for the angle of elevation, okay, now we should also note here, we should put in the parallel line through the person, okay, that is parallel to the ground, because this will be the angle of elevation. And we are told that the angle of elevation to the top of the monument is 15 degrees. So what I've done here is I've formed one triangle. We're also told that the person can look to the bottom of the monument, and the angle of depression, that is going down, is 2 degrees. So we formed another triangle. Okay. And the question is how far apart are the person and the monument? So that is our unknown distance. So let's rewrite these, what we can see about these. Here's one angle, or one triangle, and here's the other triangle. So the angle of depression here is 2 degrees. The angle of elevation here is 15 degrees. We're looking for the distance and how far apart these are. That is unknown, but it has to be the same in both triangles. Okay, this line represents the same in here. Okay. Now, I don't know how big this y1 is, this side is, and this y2 is, but I do know something about y1 and y2. They're representing the height of the monument. So I do know that y1 plus y2 must be equal to 200 feet. I do know that. But we're not looking for the y's. Remember, we're looking for the x's. Okay. So let's begin and see what we can start writing down. It might be easier to think about it this way then. We could solve this for y2. We know that y2 is 200 minus y1. If I was to subtract y1 from both sides. Okay. So maybe just to get rid of an extra variable, we'll call this 200 minus y1. Because if we add these together, they need to equal 200. Okay. Let's see, these are also right triangles. We know that. Okay. And we're looking for x. Okay, let's begin. Let's say something about this. So we know then the tangent would be y1 over x. So let's use the cotangent of 15 degrees. Would be equal to x over y1. So that would mean if I multiply both sides by y1, this would cancel. Okay. So we have that y1 is equal to the cotangent of 15 degrees. Okay. We know that to be true. Now over here, opposite over adjacent, right? So did I do that right? Opposite over adjacent. Yeah, opposite. So we want to do the same thing. We'd like to look at the cotangent of 2 degrees. Okay, so if the tangent is the opposite over the adjacent, this is x over 200 minus y1. Now, I want to get to x by itself, so let's multiply through by that denominator. Have to do that on both sides. Then these will cancel. So we have that x must be equal to 200 minus minus y1 times the cotangent of 2 degrees. I'm sorry, you guys, I didn't write this correctly, did I? This is y1 times the cotangent of 15 degrees is equal to x. Sorry about that. Okay, this value is equal to x. Okay, and then let's distribute this here. Okay, because the cotangent of 2 degrees is a constant. It's an irrational number. But let's distribute it. So this is 200 times the cotangent of 2 degrees. Do not forget your degree symbols. Okay. Minus y1 times the cotangent of 2 degrees is equal to x. Okay, so x is what we're looking for. Okay. And we have two values for x. So the trouble is, we just don't know what y1 is. Okay. If we could find out what y1 is, then we would have an exact value. Okay. But we don't have to worry. Okay. So if this is equal to x, and this is equal to x, well, then they have to be equal to each other. That is y1 times the cotangent of 15 degrees has to be equal to 200 times the cotangent of 2 degrees minus y1 times the cotangent of 2 degrees. And now this we can solve because we have one equation with one variable. Now, this variable is on both sides of the equation. Okay, so we're going to do what we did when we solved for rationals. Okay, move the term with the make sure that both the variables are on one side. So in this case, I have to move this term over. So I'm going to add y1 cotangent of 2 degrees to both sides. Now why that's helpful then is because now that the y1s are on the same side, okay, they are a common factor, so I can factor that out, and I'll be left with the cotangent of 15 degrees plus the cotangent of 2 degrees is equal to the 200 cotangent of 2 degrees. And now we can just undo what's happening and divide through by this cotangent of 15 degrees plus the cotangent of 2 degrees on both sides. Now these will cancel. And as an exact answer, y1 is equal to 200 cotangent 2 degrees over the cotangent of 15 degrees plus the cotangent of 2 degrees. Okay, so this is what y1 equals. But that's not what we were looking for, right? We were trying to find x. So the simple way that we're going to find this then is we had two formulas. One was y1 was the cotangent of 15 degrees is equal to x. The other was longer. We'll use the shorter one. So I have to multiply cotangent of 15 degrees by this. So we have that x is equal to, well, if I multiply by the cotangent of 15, we copy this, 200 cotangent of 2 degrees, and now we multiply that by the cotangent of 15 degrees over the cotangent of 15 degrees plus the cotangent of 2 degrees. And this as an exact value is how far away that person is from the monument. Okay, that is exactly how 301 works in your book. Okay, so please be following along with this step by step as you're doing number 301. Okay. That will conclude our lecture today. Email me if you have any questions.